Hi, I'm Dr. Ashley Streig. I'm a professor at Portland State University. I'm an earthquake geologist and a paleoseismologist. I work on ancient earthquakes to understand hazard associated with modern faults and modern earthquakes. Carbon is a clock in geology. We use it to understand the timing of sediments when they were deposited or laid down in things like alluvial fans or as we build up sediments around streams. I use it in my research to understand the timing of past earthquakes. So carbon is pretty unique in that we have two stable versions of carbon, carbon 12 and carbon 13. And we have an unstable carbon, carbon 14, and that's the clock. It has a radioactive decay, and that allows us to use its half-life to understand the timing of organic sediments that are incorporated in geologic deposits. So as an earthquake geologist, I look at sedimentary deposits that are faulted by active structures, active faults that build mountain ranges, faults that accommodate plate tectonic motions. Those faults are generally hazards where we have large populations that live near them. So we want to understand how large of a magnitude a fault can create, magnitude earthquake, and we want to understand how frequently those earthquakes have happened in the past so that we understand what that hazard is associated with a fault today. Carbon 14 is excellent because we can find things like detrital charcoal or needles and leaves from trees, and we can find those organic samples and we can date them and understand what that time period is that's captured by deposition of those sediments. As a geologist, we talk about layer cake stratigraphy. So the idea that you have sediments that are deposited in flat-lying layers. You can imagine that that happens over time, slowly building lots and lots of distinct flat-lying layers. And then we have a fault that ruptures and displaces the surface. All of those flat-lying layers are suddenly offset, and we can follow those truncations. We can follow the uppermost layer that's offset, and we know that's the timing of an earthquake. So I can find carbon in the layers that are offset and carbon in the layers that are not offset, and I can narrow down the window of time in which an earthquake occurred. If we want to say that an earthquake occurs on a certain fault every 200 years, we need to have really good resolution of the timing of those earthquakes. And we can do that by getting radiometric dates from carbon 14. As we all know, carbon concentrations have fluctuated in the atmosphere through time. And so we have some pretty cool tools that we use in addition to carbon 14. So we know carbon concentration has fluctuated. So a simple radioactive decay curve doesn't quite work for carbon 14. We use carbon records from old growth trees globally. We use those same type of carbon records from lake sediments that deposit annually. So anything with an annual kind of growth ring, also cave deposits like speleothems, we can date the carbon in each of those to understand where we are in time and correct for that fluctuation of carbon. But for earthquakes, we really generally have sedimentary records that are 20,000 years, sometimes a little bit more. And so carbon 14 is the perfect tool to try to narrow down that window of time of when past earthquakes have occurred. Earthquake geology is incredibly useful in engineering and in building resilient structures for large magnitude earthquakes. So we can understand that the timing, how frequently, by excavating a single paleoseismic site, so one trench across a fault or a series of trenches. When we really want to understand the length of rupture, we start tying together that type of information along the length of an entire fault. So faults can be anywhere from, 50 kilometers long to several hundred kilometers long. So we have these same types of studies that occur along the length of the fault. And we try to tie together that paleoseismic information on the frequency of those earthquakes. And the shorter in magnitude, so when we start finding where we can only associate ruptures between a few paleoseismic sites, we know that we're looking at a smaller magnitude earthquake. So that's where it becomes really, really important for us to tie down how well we can correlate ruptures or prehistoric ruptures at different sites all along the length of a fault. So carbon 14 as a tool, as a clock, is used by paleoseismologists, but not uniquely by us. Archaeologists also use this to understand the timing of deposits within civilized areas. So there's a really cool crossover between earthquake geology and archaeology in a field called archaeoseismology. So both of our fields use this awesome clock that nicely records the timing of the last 60,000 years. And there's a little bit of crossover when we find archaeological sites that may have been knocked over by an earthquake. So we can start tying together our fields of research And it works really well because we use the same clock to understand the timing of those prehistoric sediments that we're excavating.